Welcome back. Today's lecture is over Chapter 5, the plate tectonics theory. We want to look at the background of that, how it became a theory, and look at what exactly it does entail, all the different boundaries, and the expression of those on Earth's surface, what we see in terms of earthquakes, volcanism, and mountain building. And so let's begin here taking a look at our theory, and we want to go back and kind of look at the history of it, where it began. So really it began as something called this hypothesis of continental drift. It was proposed by a gentleman, Alfred Wegener, back in 1950. And his idea was that all of the continents, and we think of our continents here, North America, South America, Africa, and so on, that they were all at one time all together in a supercontinent all together, land all together, called Pangaea. So his name for that was Pangaea. Was Alfred Wegener's supercontinent Pangaea, and that those continents, Pangaea, began to break up some 200 million years ago, and now we see the continents in the position that they are now, so that they drifted. So his idea of continental drift, he called it. Continental drift hypothesis, that they began about 200 million years ago breaking up and moved into their positions that they are now. So this was his beginning kind of theory, his idea that he had, and not everyone was on board with it. He had lots of good evidence that we'll go through. It really wasn't until about 1960. So he proposed this in about 1915, and it really wasn't until about 1960 when a little more evidence came along that this then got transformed into a theory. This is sort of the overarching theory in geology that makes geology make sense, sort of the paradigm that we work in for geology. Similar to something like the natural selection would be for biological evolution. It makes it make sense. As well as, say, in astronomy, the Big Bang Theory. It's what makes the origin and the development of the universe make sense. And so continental drift, the plate tectonics theory, is sort of an overarching theory that is used in geology. So this begins with then Wegener, okay? And so there's a picture of where all the continents are together. You may not be able to see it, but again, you do have these PowerPoints available to you on Blackboard. North America, South America, Africa, Europe, Eurasia, well, Asia, Antarctica, and Australia, all together. Pangaea, he called that. All land together is what that translates into. So his hypothesis was that the continents then somehow drifted to their present positions. And so he did collect quite a bit of evidence for this, really good evidence. But map makers, maps like these, beautiful maps here, they really did already kind of recognize that, Africa right here actually would fit in, okay? That fit between Africa and South America, it looked like pieces of a jigsaw puzzle. So sort of the fit of the continents. It looks as though, yeah, at one time they were together and now they've moved apart. So the fit of the continents was a piece of the puzzle, a piece of the evidence in there. Fossil evidence, so I brought a couple, a replica of a fossil in there, but there was an organism called Mesosaurus, and it was a little 2 to 3 foot reptile, kind of a freshwater reptile that was found, okay, in South America as well as in Africa. This little freshwater organism, only just a few feet long, was not going to be capable of crossing an ocean, which is very salty, to get to Africa by swimming. And so finding this organism, Mesosaurus, on both of those continents, nowadays separated by an ocean, the Atlantic Ocean, to find them, so the fossil evidence, to find that same organism on those 2 separate continents, that was good evidence that, yeah, at one time, South America and Africa were actually together. So that organism again, Mesosaurus. Sort of a freshwater reptile. Got something here. This is a replica. Don't know how well that's going to show up under the camera here. See if we can get most of him in here. Get a feel for it. So he's like belly up here, so you're looking at the underneath of his mouth here, his rib cage and so on there, and he's got a tail that's kind of wrapping around here. So he's just kind of belly up there. But this is the Mesosaurus, okay, a little freshwater reptile that was found on both of these continents, okay, an ocean apart. That was one very important fossil type of evidence that connected the 2 continents, and this idea that they were all once together and then they separated or drifted apart. Another one I have is sort of a fern-like plant, okay, called Glossopteris, that also found in some locations that typically this was a kind of a warm climate type of a organism here, plant. So I've got this little fern in there. So some fossil evidence, Glossopteris was another one here that they mention in your book. Fern-like plant, so that was a plant. This was a reptile. Okay. Again, found in areas where the seeds of it really weren't going to blow that far, kind of larger seeds to them, so that they couldn't have blown that far. But they were found in locations crossing oceans and continents. And so their thought was that, yes, this would connect our continents as well. So a little bit of fossil evidence that he was able to find, Wagner was. Kind of getting a connection there between, oops, keep going forward too much here. Way forward. Sorry, that really went out of bounds there. Here we go. Right there, it's back to the fossil evidence and there. So that was just a couple of things that he was able to connect up to try to support his hypothesis. Rock type and structural similarities. So they looked at the mountain barriers, these mountain chains that we find, like the Appalachian Mountains beginning here in the United States, North America, but also continuing over there in Europe. And so it just seems like we have these mountain chains that connect up on different continents, which it would make sense if they were forming when all of the continents were together in our supercontinent Pangaea, and they formed then, and then the continents drifted apart. And now that is why, it's a good explanation as to why we're seeing these similar rock types and structures on separate continents, separated by ocean. Okay, so that was another thing that he looked at. And then the paleoclimatic evidence. Wegener was a meteorologist, and so he did study past climates, so ancient climates. Paleo means ancient, climatic, so studying of the climate, so meteorology, part of that. And he studied glaciers. He loved studying glaciers. He was out on the Greenland ice sheet, studying his rocks and glaciers. And so he was able to look at the glaciers, and so there's evidence in rocks of glaciation, because glaciers, as I mentioned before in the weathering process that we talked about in our sedimentary rocks, that glaciers do move and transport a lot of sediment, large pieces of sediment, and they will leave scratch marks on the rocks. And so this rock here, now you can't get your hands on this, but I've got an arrow here in the direction that the glacier was moving. We kind of call it glacial polishing. It will really scratch up and polish the rocks. It's very smooth in the direction that the glacier went, and it's very kind of, my fingernails are getting caught on it against that. And so he could tell which direction the glaciers were going, okay, by studying the rocks. And so he was able to set up different directions of where the glaciers would have been. Even finding some things in this tropical region that had glaciers on it. So that kind of tells us right there that these continents, when they were together as Pangaea, back to that some of these continents were closer to the poles, okay? Look up here. Closer to the poles, to where it would have been cold enough to actually have glaciers. And so he could look at the direction in the rocks that these glaciers were scratching, and he could really figure out where the glacier was, and then which way these continents would have drifted when they drifted apart. Okay, and so all that kind of together is some really strong evidence for his continental drift hypothesis. Okay. But at first, he had a little difficulty trying to explain, well, just how are those continents moving through the ocean? You know, what was the mechanism? And he had a little bit of trouble with that mechanism. But here was a nice little picture of the matching of the rock types and the rock structures. Here's our mountain range that I was mentioning. Here, you know, the Appalachian Mountains here, but it continues on over those same rocks and same structures up over here into Europe, way up in there, even up near Greenland. It's like an extension of it. We see that same mountain chain over here in Africa. So if at one time these were all together and they built up the mountains and then drifted apart, it would make sense that we're seeing those same rock types, those same mountain structures, okay, the mountain ranges that match, okay. In North America, there's Africa, Europe, Greenland, where we have a mountain chain all along there that do match, okay. And so good piece of the evidence there. And then that paleoclimatic evidence. So the scratches on the rocks, so the geology, that study of paleoclimate through looking at rocks, how the glaciers scratch the rocks, okay? And so these little arrows, you may not be able to see them too well on the PowerPoint, but they're showing, there's a little bit of snow there, meaning glaciated, where you see little arrows. That's telling us the direction that the glacier was going through the rock evidence that we see, okay? Could tell those directions. And so when he put it all back together, okay, if all your continents were together, here's one big glacier near the pole there, and glaciers just sort of spread out in all directions, right, when they move. And so all of those scratches that they were making, okay, when the land was all together, his Pangea, when they were all together, and then drifted apart. That's why we're seeing in the rock record, okay, way up here, okay, in South America, where there were glaciers at one time, okay, in the rock record. And so that was that paleoclimatic evidence that we mentioned just a minute ago. Nice little picture of that in there. But like I said, he did encounter some skeptics with his hypothesis when he did present it. It was just how exactly were those continents plowing through the crust. And so if you remember from our talk about the rocks, the oceanic crust is a basaltic, so this is my piece of basalt here, type of rock, okay, material. So it is a little more dense. It is going to be one that would, if these were to meet up, be the one that would go underneath or subduct. So it's a little more dense. It's a dark rock. It's got a lot of magnesium and iron in it, so silicate. And then the oceanic, or the continental crust, if you remember, was more of a granite type, so a granitic one, a little bit of the lighter silicate minerals in this one. So a granite, this would be more like continental crust, less dense. So you've got the oceanic crust, basaltic, versus the granitic or the continental crust. So we do have some differences in the crust. And he's like, well, how were these continents going through that oceanic crust? What was your mechanism? So his idea was that the continents, the granitic continents material, was more or less plowing through the denser basaltic oceanic crust due to tidal forces, like the sun and the moon creating tides. Well, those forces do create tides in water, but the force is not strong enough to take a continent and move it through the oceanic crust. And so there was a leading physicist at the time, and he said, no, that could not be possible. If you had a force that strong, the tidal force is that strong, it would actually stop the rotation of the Earth, and that hasn't happened. Plus, you should see evidence of extreme stress on the rocks should they have been plowing through, almost like an icebreaker, through, ice, if that crust was going through the oceanic crust like that. So we don't have evidence of that. And so that physicist of the time, when you're presenting a hypothesis, it is refereed and reviewed, and it does have to be consistent with all branches of science. You can't go against the laws of physics and things like that. So that was not a plausible mechanism that he came up with. And so for that reason, it was not accepted right away. Okay, so his ideas were plausible, right, but it did contained some incorrect details on the mechanism. So the mechanism really gave him some trouble in trying to explain. So it didn't really catch on too well. But about 1930, Wegener, he was out on the Greenland ice sheet doing what he loves, studying the glaciers, and he died out there. And so about 1930, 15 years after he proposed his continental drift, he died, but his ideas did not die with him. So, you know, we're getting towards 1930s now. We've got World War I about going on in the 1930s, and not a lot of effort was put towards scientific research. So his idea here kind of got put on hold a little bit. And so it didn't completely die. There were people who definitely thought it was very plausible. But one little thing that did come out of the World War I, if it was anything good that came out of that, was that we studied the ocean floor. And so we began with sonar waves, kind of studying the ocean because we needed to know what was down there. We were looking for submarines and things like that, so because of the war. But a Princeton geologist, Harry Hess was his name, he noticed in the seafloor, as we were studying the seafloor, that there was quite a topography there, the shape of the land. There were mountain ranges there. There were places where the ocean floor was spreading apart and new crust was forming within it. So the seafloor was actually spreading. So this idea of the seafloor spreading through plate tectonics here really gave us our mechanism. So we do thank Harry Hess for that. We'll write his name down. Seafloor spreading. Idea of seafloor spreading, where new crust was actually welling up beneath there, creating little mountain ranges in there. Right down through here, the mid-Atlantic kind of ridge where we've got a mountain range going right through the Atlantic Ocean. And so there's a spreading center where new magma is welling up and creating new crust, so a ridge beneath there, and it wheedles its way, winds its way through the Atlantic Ocean there. So here we go. Here's our mechanism. Seafloor spreading. You're getting new crust forming in the middle, but all the while, as this ocean is spreading and creating new crust along the ridge, okay, the continents are drifting, the continents are moving apart. They did some more studies along the ridge there of kind of age dating them, radiometrically kind of age dating the rocks there. And they did notice that right along the ridge where the new crust was forming, that was very young rock material. And then as you moved farther and farther away from the spreading center, you do see older and older rock ages, like a mirror image on each side of the ridge. So youngest here, a little bit older, a little bit older, a little bit older as you go away from it. So this was the clincher here that did finally give the mechanism to Alfred Wegener's continental drift hypothesis. Perfect for this, although he had already passed away. So his principle was correct. He had the problem with the mechanism. It wasn't tidal forces. And so the research did kind of get put on hold, but then came to life with the seafloor spreading information. that came to life. Okay, diverging, pulling apart of the crust. Okay, so these rifts, forming rifts. Okay. And they also kind of studied the age of the seafloors as well. So all along, this continental drift hypothesis melded into and sort of became the modern now plate tectonics theory that we talk about and study today. And it really kind of caught on around the 1960s. It almost went, within a matter of 5 years, being not plausible, forget about it, to being totally plausible with the seafloor spreading idea, and everybody wanted to write a paper about it, and they did, to becoming the most hot topic in the 1960s. And so what a matter of just a few years in there did once they had their mechanism. So fantastic. It evolved kind of into that theory of plate tectonics. So the plate tectonics is a modern version of that old idea of continental drift. So Wegener was onto something there. And to where we have Earth's kind of major plates, and there's really probably about 7 major plates or so, with a lot of little minor ones in there as well. But associated with the Earth's outer rigid layer, we do call that the lithosphere. Okay. Lithosphere, litho. You've heard that term when we talked about the sedimentary rocks, the lithification process. So turning to stone, basically. Lithosphere, so rigid outer portion. So it consists of the uppermost mantle and then the overlying crust, which is oceanic and continental crust. We have 2 types of crust. And it overlies then a weaker region in the mantle that we call the asthenosphere. The asthenosphere is one that actually flows, okay? I always liken this to an egg, a raw egg. If you think about the outer shell, the brittle outer shell of an egg, that would be the lithosphere, and beneath it all the gooey egg white, which can flow, right? It's still kind of solid, but it flows. And that is what we would liken to the asthenosphere. So the asthenosphere actually does flow, okay? And so here you have the rigid plates kind of flowing along this weaker kind of zone in there within the mantle called the asthenosphere. So here the plates are floating and moving along the asthenosphere in there. So kind of a hot plastic-like layer where it will flow. That's the asthenosphere. Okay. So it allows for the movement of Earth's crust, the asthenosphere does. 7 major, again, like I said, lithospheric plates. These plates are in motion continuously. We have a very, very dynamic planet. It is always in motion. And so continuously moving. They are changing in shape and size as they do move. Our largest plate is the Pacific plate. Several plates include an entire continent plus a large area of the seafloor. So it's not that our plates are a continent by itself. No, the plates can be a continent plus some of the seafloor out there underneath the ocean. So it's not that these, one single continent is a plate. That's not how it works. So a plate can be, like including a continent plus some of the seafloor. So 7 major ones, but some smaller, minor ones as well. But that's important to remember, is that it's not just one continent, it's part of the ocean floor as well, and that whole thing is moving along on the asthenosphere. Okay, so that's sort of showing some of the plates in there. The Eurasian plate, the Arabian plate, the African, East African, the rift zone in there, the Australian Indian plate. So here we've got a couple continents on that. Here's the Pacific plate. So out there underneath the ocean, part of the Pacific plate here. It actually continues on the other side of my map, which I don't think you can see the whole map there. But as that is moving, as that crust is moving, and you see the arrows pulling apart, diverging, coming apart, you see some molten magma welling up and creating new crust all along that spreading center. Okay, so that's a divergent boundary there, allowing magma to well up. Okay, and we'll look at our different boundaries. But this really will explain a lot of our volcanism, right? So the upwelling of the magma. It also explains the plate motion of these boundaries, explains the seismic activity, meaning earthquakes, that activity, and it also explains mountain building. So all in a nutshell, the plate tectonics theory explains, because of the motion of the crust, it explains our volcanism, why we see it, where we see it, explains our earthquakes, so our seismic activity, and it explains the mountain building, why we're seeing mountains, where we see them. It's all because of the interaction of Earth's plates, these 7 major plates. So the movement, the building, the tectonics of these plates. And that's just showing a few more here. Here we happen to have crust coming together. So we've got a continent here, and we've got an oceanic crust, and they're coming together. So this would be a converging type of a plate boundary, where the boundary of 2 plates come together, converge. Well, I mentioned that the oceanic crust, okay, the basaltic type of crust, versus the granitic or continental type of crust have differences in their physical composition, one thing, but their densities, that changes up their densities. So the oceanic crust is a more dense crust, a heavier crust, than the lighter, less dense continental crust, the granitic crust. And so because of those density differences, we do get, when those two come together and converge, the denser oceanic crust is going to subduct. So there's a subduction zone, go down below, subduct, downward, okay? And the oceanic crust is above here. And so what that picture's showing is that the heavier continental crust is subducting beneath, and as it does that, it's getting destroyed. It's kind of like a recycling center. And the outward expression then, so as that goes down, creating lots of friction, a lot of heating is happening as it's plunging beneath the other crust, and you're starting to see little magma, a little picture of magma welling up. And the expression on the surface of that convergent kind of coming together boundary is these continental volcanic arcs. And so we're creating arcs of volcanoes on the continents, okay, in a convergent boundary. A little ways out in the ocean here, right where that's subducted, that subduction zone, you see what we call a trench. So these deep trenches, as that crust is plunging below, the surface of that is called a trench. And so that's sort of the anatomy of a convergent plate boundary of what we would see. And they're showing you the Nazca plate and the South American plates coming together. So part of the Pacific plate out there, this would be ocean crust versus a continental crust. And you do see a very deep trench. I'll try to do some Google Earth for us on this, but there's a trench right out there on the west coast of South America. Another one over here is where you're getting a type of boundary where the crust isn't pulling apart and it's not coming together. It's just kind of sliding past one another in a shearing kind of fashion. We call those a transform type of a boundary. They're just kind of grazing past one another. You're not going to get volcanism volcanoes with a transform boundary, but you will get the earthquakes, the seismic activity. But because of these different plate boundaries, that really does explain the seismic activity, the volcanism, and the mountain building. Earth's crust moving. Those plates are moving. So they do move relative to one another, a very slow but very continuous rate. So there are some places that we're creating crust, other places that we're destroying crust. So matter's neither created nor destroyed, and so it's sort of a recycling and renewal type of scenario happening. Earth's circumference, so its diameter, is not getting any larger or smaller. So there is a balance between the development of new crust and the recycling or destroying of crust, okay? And so this back and forth balance between it. So they're mentioning here the cooler, denser slabs of the oceanic crust, so that basaltic type of crust, is the one that's going to descend down into the mantle material and get recycled because it's the denser one. So here we have our list of our plate boundaries, the interactions among the individual boundaries there. And so again, remember, it's not just one continent on there. You've got part of the ocean even just around your continent for these. But we have three main types that we talk about. The divergent plate boundaries mean pulling apart. Diverge, to pull apart, move apart. That's the divergent plate boundary. And that one's constructive, they call it. A constructive margin, because that's where you're going to get the upwelling of the magma and create new crust. So constructive. Then we have a convergent plate boundary. Convergent meaning coming together, moving together. These are destructive, right? Because that more dense oceanic crust is going to subduct beneath that lighter oceanic crust, okay? So that's a convergent margin, destructive. And transform fault boundaries, they do call those conservative because crust is neither created nor destroyed during a transform, and so those are just sort of shearing or sliding past one another like that, okay? So conservative, they mention in that one. So they don't destroy or create crust in a transform boundary. So here we have the divergent plate boundary. So the first one that they're going to talk about, divergent, so the pulling apart of the crust. I have a little picture that sort of had those, some of those on there. Maybe you want to draw a picture in your notes. You can see that where I'm using a few of those terms, convergent and divergent, but beneath the Earth's crust, within the mantle material, we have what we call these convection cells. So circular kind of motion. Recall that the internal part of the Earth is molten, and all that heat's trying to make its way out from where it's very hot in the interior of the Earth to where it gets cooler as you go outwards. So that heat's trying to make its way out, and it does create these convection cells. And so here I have a convection cell moving upward, and so looking at how those happen to come together, here we have one where two arrows are coming together, and so that's convergent. That would be a convergent boundary, and this is destructive. So that's where one, I've got one crust will be going over, the other one, the oceanic crust, the more dense one, will be going under, okay, and destroying crust there. So this is sort of the recycling center, is what I put there. In this scenario, we've got one coming up and going that way, and one coming up and going that way, moving the plates apart. So So divergent, okay? And in the divergent, it actually pulls the crust apart. We call it a rift, right? So I've got a little rift here. And then you get the upwelling of the magma, that molten kind of material, and it's filling in, creating new crust. And so those are called constructive, and you get the development of new crust in there. So in this manner, we are destroying crust in some places along boundaries that are convergent, but creating crust in other places that in locations where the boundaries are divergent. And so there is a nice balance between those. So maybe get a chance to draw that out for yourself so you can see the interaction between divergent and convergent. So divergent is the first one we want to talk about. Located along, most of these along the oceanic ridges, and I mentioned the Atlantic ridge, the mid-Atlantic ridge is probably the most studied ridge, but divergent because that magma is welling up along there. So oceanic ridges associated with that sea floor spreading that our Harry Hess, Princeton geologist, came up with, the sea floor spreading. So along well-developed divergent boundaries, that sea floor becomes elevated, creating these oceanic ridges. And so, yeah, the mid-Atlantic ocean ridge is coming from that seafloor spreading. Let me try to go to Google Earth, see if we can get it to work for us. See if it's going to show up for us. Okay, so for orientation here, of course we've got the United States, so North America up here. And so out in the middle here would be the Atlantic Ocean. So North America, and I'm aiming for right along here in the mid-Atlantic Ocean. Iceland, so Iceland on my map here is right located there. Iceland is actually right over that mid-Atlantic ridge. So most of the ridge is beneath the ocean. But in some places where the upwelling of the material crust has gone above the ocean surface, well, we get little old Iceland out there. And Iceland is right there on the mid-Atlantic ridge there. So put it a little bit bigger so you can see maybe. Maybe you're seeing this, I'm not sure. But we do have that ridge kind of coming along, spreading and spreading, kind of winding its way through the ocean. Oh, I keep following it here. And eventually I get the ridge coming along. We get to Iceland. And so we've got the Eurasian plate and the North American plates, and there's a divergent spreading center there, and enough welling came up and created Iceland there. So Iceland is actually getting a little bit bigger as you go. So Iceland is located over the mid-Atlantic ridge, and I've kind of got a picture here as well. Iceland right over the ridge. Okay. So yeah, here's our mid-Atlantic ridge making its way. You see a lot of, you may not be able to see this very well, but there's a lot of little crosshatch marks on there, almost like the stitches on a baseball as it's going around a curved surface. Because the Earth is a sphere, and we are spreading on that sphere, so we get little offsets of those transform boundaries that we'll talk about in a bit. So, but it winds its way through the ocean, the mid-Atlantic Ocean, and there sits Iceland, where the crust has actually built up high enough to go above sea level. And this picture here is just showing that they built a little pathway that you could walk down, and on one side of it is North American plate, and on the other side of it is the Eurasian plate. And so you're like on two different plates. You're right on the mid-Atlantic ridge. And so, yeah, Iceland keeps getting bigger and bigger. The Atlantic Ocean keeps getting bigger and bigger as we get that spreading center there. So these are divergent plate boundaries. Okay. So that is a kind of oceanic divergent plate boundary. Yeah, so Iceland is right over the mid-Atlantic. We can get divergent plate boundaries also within a continent. So the African continent of Africa has this little rift. I'm not sure how well you'll see it from my map there, but let me go over that way on Google Earth. We can see it any better there. Let's go over to Africa. Africa straight down here. Okay. But right in here, so here's the continent of Africa. Right in there, okay, we have where the continent rifted apart. So it is a divergent boundary in there that is pulling apart the continent. So continental divergent, pulling apart. We call that the East African Rift Valley. So a divergent boundary in there. This area in here was written about by a famous author, 20th century author, Ernest Hemingway, who for a while lived in Arkansas, believe it or not, in Piggott, Arkansas, where he did some of his writing. That's in northern Arkansas, Piggott, Arkansas. And he wrote a sort of a safari, African safari type of a novel, but it was called The Snows of Kilimanjaro. And so Kilimanjaro is like the tallest mountain in Africa, and so sort of that safari type of a vibe to his story. But yeah, Ernest Hemingway actually spent some time here in Arkansas doing some writing. They even have a little museum in the loft kind of area where he did his writing. But Ernest Hemingway, interestingly enough, has a connection to Arkansas, which has a connection to our East African Rift Valley in there, a divergent plate boundary. So who knew how geology was going to come together? But the snows of Kilimanjaro. Okay, I got a little picture of Mount Kilimanjaro for you. Will maybe help you remember Ernest Hemingway, the kind of 20th century author, famous author. And so the snows of Kilimanjaro is what he was referring to in that East African Rift Valley area, divergent plate boundary. I think the snows of Kilimanjaro are melting with our climate change, so in there. So those were some divergent, and so you can see when I've got my little fault blocks here, when I pull apart, so divergent, when I pull apart, notice how the crust drops down in the center. Okay, so that rifting or that pulling apart, yeah, will cause a drop down of the land. Okay, we have some of that a little closer to home, not just in Africa there, where there's a rift in New Mexico, Taos, New Mexico, where we have the Rio Grande. Okay, and they actually try to put a bridge across there, but because it is continuing to diverge, they have to always go in and kind of reconfigure it to allow for the spread there. But the Rio Grande Gorge Bridge. Okay, so I've got a picture there of that. So in Taos, New Mexico, in there. So we've got a lot of kind of basaltic material here in the layers, layer after layer after layer of that. And so that land is rifting a bit, even here in sort of our western part of the United States. And so even within a continent, you can get these divergent types of boundaries. So closer to home there. Let's take a look. So that East African kind of Rift Valley, that's where the Red Sea is. A little bit of that water gets inland into there, okay, and that's known as the Red Sea in that East African kind of Rift Valley. Recently formed kind of divergent plate boundary in there. Yeah, and then in North America, that active one in New Mexico, Taos, New Mexico. So these were kind of the divergent variety of plate boundary. Okay. Let's see if we can get back to our points there. Mostly they do wind their way, they're out in the Pacific Ocean too, these divergent boundaries. But the most studied one is probably the Mid-Atlantic Ridge divergent boundary. Okay, so yeah, we've got the seafloor spreading occurring along the oceanic ridge system. And so spreading rates and ridge topography, so that term topography means the shape of the land, so what's going on with the shape of the land, and beneath the ocean there's quite a lot of topography going on there. So we do have some topography differences. They're controlled by the spreading rates, and so I was mentioning how we're on a sphere and it sort of has these offset, almost look like stitches, but those are those transform boundaries where things are just shearing across from one another. So. And there's a nice picture again. So you've got your oceanic crust spreading apart, magma coming up in the center. So a very famous one is the Mid-Atlantic Ridge. Okay, you see how that one's going that way, that one's going that way, so divergent. Mid-Atlantic Ridge is a great example of that one. Mentioned the land rifting apart here. Two or more segments are rifting apart, continental rift. So East African Rift Valley that I showed you, of the snows of Mount Kilimanjaro, and Ernest Hemingway is a good one. The Rhine Valley in Northern Europe is another one. And I mentioned the one here in the United States in New Mexico, Taos, New Mexico, the Rio Grande Bridge. That I was showing you there, the gorge, produced by extensional forces. So extensional forces are the pulling apart of the lithospheric plates. So I've got the plates and actually pulling apart, and so you get that drop down, that rifting, okay, drop down, rifting occurring. So extensional forces, meaning pulling apart, extension or tension. We do call that pulling apart, acting on the plates, okay, the lithospheric plates, so the crust and that little uppermost part of the mantle, that's the lithosphere. Okay, so continental rifting, so here we've got a continent rifting apart as well, and they sort of show you the series. And then the point where water's starting to kind of get in there as well with the Red Sea. It's a good example of that. So those were all divergent plate boundaries. Now I want to go the other way. I want to converge, come together. So convergent plate boundaries, there's three types of convergent plate boundaries. But here, older portions of, say, oceanic crust gets returned to the mantle. So this is a destructive process, if you recall, where crust is going to get recycled. So it's going to get destroyed. Okay. surface expression of the descending plate. So I mentioned out along South American's coast here, okay, where these are converging, Pacific plate, South American plate are converging. Well, that oceanic crust is going to be the one that goes under and subducts. So subduction zone here, a subduction zone. And you will see, just a little ways off the continent there, a very deep ocean trench. When we look at Google Earth on this, get there real quick, bring that back up. Let's go back over to South America. So South America there, just a little ways off of the continent, you see a much darker, almost black line here, okay, beneath the ocean. So that is a trench, a deep ocean trench, we call that. That's the location then where the subduction zone is, and it gets expressed as a trench. We call that a deep ocean trench. Okay. So we got the ocean trench associated with that subduction zone in there. And they talk about an average kind of subduction angle of about 45 degrees, give or take. But yeah, where the continents or the plate boundaries are coming together, this is convergence. And certainly one is going to descend beneath the other one, especially if you have oceanic and continental. The oceanic crust is the one that's going to subduct and go down because it's the more dense crust, okay, leaving the continental crust to be the one that overrides. Okay. So oceanic, continental is our first type. Remember, there's three types. Okay. Denser oceanic slab sinks below into the asthenosphere, right? That very fluid moving asthenosphere, plastic-like. Along that descending plate, you get some partial magma beginning to melt in there, mantle generating the magma. And because of that, we get what we call a continental volcanic arc. And so you're going to get, we mentioned South America there, along here, along the continental border there, you're going to see lots of volcanism, tremendous amount of volcanism in that region. We also have on the west coast of the United States, okay, this is another convergent plate boundary, the North American plate and the Pacific plate coming together, so that oceanic Pacific plate descends under the North American plate and along our west coast, okay? That is where we have our volcanoes, that volcanism. So that's the continental volcanic arc. That's the outward surface expression of a oceanic continental convergent plate boundary. Good examples are the Andes Mountains along South America and the Cascades Mountains in the along North America there, our west coast of the United States, the Cascades Mountains, Mount Rainier and such. So volcanism is an expression, a surface expression of the oceanic continental plate boundaries. So Andes Mountains as well as the Cascades Mountains. There's a nice picture, oceanic continental still. Okay, looking at that one. Those density differences, yeah, you are going to get subducting of the oceanic crust. That's going to create the melting, which gives the upwelling then to create those continental volcanic arcs on the continent. Okay, and outwards here, you're going to see right at that subduction zone those oceanic trenches, those deep oceanic trenches. You can actually get some very deep oceanic trenches out there. I think of the Mariana Trench. That's a very deep one. Some of the deepest parts of the ocean are there. Okay, again, they're continuing. It's still oceanic, oceanic. One's descending. Now we're moving on to the second type, oceanic, oceanic. So now we have both crusts that are oceanic but coming together. Okay, remember, it's not always you have a continent that's at a boundary. That's not how it works. Sometimes you can have it within the ocean, two plates, oceanic and oceanic, that converge. But because they have pretty similar densities, and one of them is going to descend here, and you're going to get volcanoes on the ocean floor. So here we're going to start to get, if they actually make their way above the ocean surface and we see them, these little volcanic island arcs. So now we get these little volcanic islands out there. So an island arc, and we do see quite a few of those. The Aleutian Islands that come off of Alaska, all these little dotted things here. Okay, those are the Aleutian Islands coming off of Alaska, where we have oceanic plates converging, okay, creating the expression on the surface, then these little island arcs, they call them. The Tonga Islands as well. Japan, so it'd be like on the other side of my map over there, you can't quite see, but the Philippines as well. All of those little islands that you have are oceanic convergent plate boundaries, and you get the volcanic island arcs out there. Okay. So yeah, that subduction zone there, along there, you're getting all the Aleutian ones off of the Alaska border there, Alaskan islands. Oceanic convergence. And the Mariana Trench is actually over on the other side of my map, but the Mariana Trenches, like I mentioned before, where the deepest parts of the ocean are so far recorded, coming from there. So here's oceanic, so we're out in the ocean. We happen to have two oceanic crusts coming together. We do get that subduction, and you're seeing the expression of that as a trench. But out here, this is out in the middle of the ocean now, where you're creating a volcanic island out there, again, because of the melting that occurs when we get that subduction zone. So that was oceanic. Here, well, how about two continents slamming together? So continental convergence. So now we've got two continents coming together. These are less dense, right? They're buoyant. The continental lithosphere does not want to subduct. Okay, and so you're going to get mountains to build up here. These aren't going to be volcanic mountains, okay? No volcanism with that because there's no subduction happening. But they're going to buckle up, okay? When the two continents come together, they're going to buckle up and create mountain blocks in here. And so the Himalayan mountains, the Alps, the Appalachians here in the United States were formed in that manner. And again, I don't think you can see that far over on the map here, but the Himalayan mountains, so when India slammed up and against Asia and continental buckled up the Himalayan mountains. So that's a continental convergence. A little closer to home, here in Arkansas, where's my good old map, the Ouachita Mountains formed from a continental convergence. So our good old Ouachita Mountains formed in this manner, where when the South American plate and the North American plates, when Pangea was assembling, so when all the land was coming together, that supercontinent, South America, North America collided, convergence, and it actually buckled up. It really did a lot of deformation, structural deformation here, even in Arkansas, in our Ouachita Mountain region. So continental convergence formed the Ouachita Mountains that we have here in Arkansas. And with my plate, my little fault blocks here, if I can bring them out. So let's say we do have our continental crust coming together, and so I'm compressing, pushing together, converging, and you see how you're getting the buckling up of the land, so the mountain building in that type, continental convergence. Okay, so a compressional type of a force coming together, converging, and it did. It buckled up and created our Ouachita Mountain region there. Good example of a continental. Okay, yeah, so Himalayas, Alps, the Appalachian mountain chains in North America, and the good old Ouachita Mountains here in Arkansas. Okay, so they're kind of showing our continental, and so you're getting both this being continental, and so it's far enough away here that we're not getting the volcanism. So Ouachita Mountains don't have any volcanism, the Himalayan mountains, the Alps, none of those ones that were mentioned before have any volcanism. Okay, it's just a buckling up of the continental crust in this type. So that's our third type of convergent plate boundaries. Okay, there were three types of the convergent. Your transform fault boundaries, as I mentioned, the Earth is a sphere. It is round, and so here you are, you're pulling apart or you're coming together, converging on a sphere, and so you will get these little offset kind of shearing motion of the crust. So they're sliding past one another. No new lithosphere is created or destroyed in the process, okay? No volcanism with these, but you do get the earthquakes, and these can be some really strong earthquakes. So yeah, your transform faults are going to join two segments of mid-ocean ridge along those breaks, and so I was saying how it was kind of looking like stitches on a baseball, all those little lines. Those are the transform faults, and so they're joining segments of the mid-ocean ridge along breaks, known as little fracture zones, and you can get a lot of seismic activity, a lot of earthquakes because of that fracturing that's happening. And so off in California, on the west coast of the United States, we do have that San Andreas fault zone, and that is a transform type of a fault, or transform type of boundary there, and so the associated earthquakes that occur with that San Andreas fault. So between the North American plate and the South American plate, so North American plate, South American plate, and you're getting a shearing kind of a motion, sliding past one another in that zone. And there is sort of a town, little geologic feature of a transform boundary. In Parkfield, California, they've done an interesting thing here where they built a bridge across the boundary, kind of interesting, over that a portion of the San Andreas Fault. It's actually very long. But here you're entering the North American plate on one side of the bridge, and here you're entering the Pacific plate. So the North American plate and the Pacific plate, and they built this bridge. Of course, they have to go in and keep fixing that bridge because of the shifting of the motion on it. But that is in Parkfield, California, And it's just a little spit of a town, but they have a little restaurant in there, if you could call it a restaurant. And their claim to fame is that they're called the earthquake capital of the world, okay, in Parkfield, California. They built a little bridge over the plates there. So at one end of it, you've got the Pacific plate, other end of it, the North American plate. So earthquake capital of the world, Parkfield, California there. The geologic feature of a transform fault there, transform fault. Transform boundary, okay. Okay, so that's just a shearing motion with our transform boundary. So no volcanism would be involved in a transform type of a fault boundary. So San Andreas Fault, as I mentioned, that's a very famous one. The Alpine Fault of New Zealand, again, cutting through, that one, cutting through a continental crust in there. So fracture zones associated with those earthquakes associated with those as well. Transform. And now we got some pictures of the transform faults. And with this, we've got some places here that they say are active and inactive, because if you look, one plate's moving that way, one plate's moving that way in a divergent boundary out there in the mid-ocean ridge, right? But these little things offset them. Off over here, it's going that way, going that way. And so, yeah, you've got an active kind of a shearing motion happening right along there, okay, where they're going in opposite directions. Here they're going in the same direction, so that's an inactive zone. Here those arrows are going in the same direction, so another inactive zone. But right in here, where that slab's going one direction and that slab's going in the opposite direction, they're shearing past one another, that's an active zone in there. And that's the transform boundary in there, an active one. Okay. And so we see that all along that little, the red ones there are the spreading centers of the mid-ocean ridge that winds its way all along the mid-ocean Atlantic ridge. But then those little transform faults, okay, in yellow there, you might not see that too well, but you do have these PowerPoints. And those were the transform ones, are offsetting that main spreading center. Okay. So those are the transform faults. So testing the plate tectonics theory. So they did need to do some testing of it. The most convincing evidence confirming the spreading of the sea floor, why we know it's really happening, okay, out there, is the ocean drilling, okay, results. So they'll go down with drills and take out a core of the oceanic crust in there, and they can study it. They can study the sediments in it, they can age date it, they can do all sorts of radioactivity tests on it, magnetic tests on it. So it's magnetic polarity, we can get that from this as well. But you're setting up the ages of the deepest sediments. The thickness of the ocean floor is varying as it's spreading. Tends to be thinnest right there where you're getting the new crust to form, which makes sense because that's the new active crust forming. As you go away from that spreading center, the sediments are going to get a little thicker because they've been there longer. The age of those rocks are going to be a little bit older of that crust on either side of your ridge, okay? And they found that evidence that as you got farther and farther away from the spreading center, the age of your rocks got older in a mirrored image on each side, and the thickness of the sediments got thicker away from the spreading center. So they've done a lot of ocean drilling where they've studied those sediments. And again, the Mid-Atlantic Ridge is the one that's really been studied the most in there. Very symmetrical on each side of that. So at one time they were together and they began to spread apart. Some more evidence that helps us sort of cinch our theory of plate tectonics, kind of testing it. These things that we call hot spots or mantle plumes. So there's just little upwellings of magma here and there beneath the Earth's surface, and they'll form, the famous one is the Hawaiian Island chain. I don't think we can maybe see it here, but Hawaiian Islands are over, had been forming over a hot spot or a mantle plume, so this magma that's welling up. And all the while, the crustal plate has been moving over that mantle plume, and so it builds up your Hawaiian Islands. And if you'll notice, in the Hawaiian Islands, it's just the island that is over the mantle plume or the hot spot that is the active volcanic island. Those islands that are a little further away from that plume are no longer active. Okay, at one point they were when they were over the hot spot, but when the plates shifted and moved, plate tectonics, the moving of the plates, they become no longer active when they move off of the hot spot. So that Hawaiian Island chain is really good evidence for the plate tectonics theory that the crust is moving over these. So the plumes are long-lived structures. Some are very, very deep, maybe even clear to the mantle core boundary in there. But this is that Hawaiian chain here, okay, along here. The main island, the big island of Hawaii, the active island is over the hot spot right now. That's why the volcanism is active. But all of these, okay, we've got the Midway Islands here, the Emperor Seamount chains there. And so they change direction, right? Because the plates tended to kind of go more of a north to a northwest kind of direction over time. And so they've got the ages of these. The present one about, and these are in millions of years, 0.7 of million years. Here's less than a million years, Maui, 1.3 to 1.8, Oahu, 2.2 to 3.3, Kauai, 3.8 to 5.6. So the age of the islands are older. So that's telling us that they have moved off of the mantle plume that built them up, and so moved along, and they can even tell kind of the direction that the plate was moving over that hot spot. And so that was some really good evidence. They're proposing that those Hawaiian Islands are forming over that hot spot. We have one a little closer to home. Here we've got a hot spot in Yellowstone National Park. There's a hot spot. Maybe you have been to Yellowstone National Park. Is over a hot spot. And so right now we're currently over there. If you think of Old Faithful, that geyser, so the heating from beneath there. Yeah, Yellowstone National Park has formed over a hot spot here in North America as well. Okay. Oh, another one kind of piece of evidence that really helped with the kind of cinching our plate tectonics was, we called that paleomagnetism. So paleo meaning ancient, magnetism. So the poles, magnetic poles that Earth is surrounded by, north and south magnetic poles. So the iron-rich minerals, remember our magnetite, those iron-rich minerals, that does have magnetism in it. Well, so the iron-rich minerals become magnetized, and when they do, depending on, you know, our North Pole, South Pole, what those magnetic poles are, the minerals in the rocks will align as they're forming, because you remember magnetite and these like that, they're kind of molten, but when they solidify, okay, out, they freeze, kind of get frozen in a particular direction according to the magnetic poles, the magnetic north and magnetic south, actually do have reversals. Several millions of years in between, but the North Pole and the South Pole do have these reversals. And so the existing magnetic field, as they crystallize, it gets frozen in the rock. And so they can go out and they can study that. Looking millions of years back, has a record of the direction of the magnetic poles at the time of their formation. And so they study that. And there was this thought that, well, are the magnetic poles wandering? Or is it that the continents, okay, the land, was actually moving and doing the wandering and not our magnetic poles kind of thing? So lava flows of different ages indicated several different magnetic poles, almost like our north and south poles were wandering all over the place. Okay. But this is more readily explained by the theory of plate tectonics. It's not that the magnetic poles are wandering, it's that the continents, the land, was wandering. Okay. And so they matched that up here, where these were what they were finding, the apparent polar wandering. This was the North American plate. Okay. Here was Eurasia. Right. And so, was it the magnetic poles that were doing that wandering, or was it that at one time all the land was together and then it began moving? Okay, the plate tectonics. And when you match that up, they match pretty well. Okay, so that's a good explanation of it. Well, wasn't the magnetic poles doing the wandering? It was the plate tectonics moving the land over time. So that was another really good set of support to this theory. So the Earth's magnetic field periodically reverses its polarity. North becomes south and south becomes north, vice versa there. Dates when polarity of the Earth's magnetism changed were determined from the lava flows, as I mentioned before. You can get that frozen in the rocks. And so these geomagnetic reversals are recorded in the ocean crust. And so kind of really helped support Harry Hess and his work of the seafloor spreading to kind of confirm that. What they were doing was these magnetic strips in the ocean crust near the ridges where Hess, meaning Harry Hess, that Princeton geologist, and his concept of seafloor spreading, it was supported by that. And so here we have periods of normal magnetism, and that you can't see these arrows probably, but they're going in a particular direction, right? The white strip versus the red strip there. So depending on when we had a magnetic reversal, again, millions of years that these take place, these reversals. At one period of time, you know, normal was the white, and then a reversal happened, the red. But what they're seeing on either side of the mid-ocean crust, that ridge, that spreading center, is an exact mirror image. So here we've got, you know, another reversal in there, another reversal in there. And so it's a mirror image on each side of our spreading center. And so at one time these were together, and that just cinches sort of the seafloor spreading mechanism that we've been talking about. So yeah, paleomagnetism is another really good supporter of the plate tectonics theory. So what's driving the plate motions? And they've got, it actually could be a combination of all of these, but some forces that are driving these. Yeah, you're probably not going to be able to see my little picture that I have. But slab pull, ridge push, and slab suction, I think we've got a picture here. There we go. So ridge pull, kind of pulling apart, slab suction, kind of coming together, and slab pull is sort of the subduction. And it's probably a combination of all of these forces creating the driving mechanism of our plate tectonics, the motion of the crust. And there's some ideas here of some models of the mantle kind of convection. I did mention and kind of drew those convection cells where we've got that molten material. It's very hot in the interior of the Earth. And so that heat's trying to make its way out, and it'll create these convection cells. So that term convection. But is it, only going maybe 660 kilometers down? Or is it involving the whole mantle? Those questions are still unanswered. We don't know how deep the convection goes. Is it a whole mantle being involved, or just, several kilometers, 100 kilometers down? So some questions are still out there for research, but all in all, the plate tectonics theory is an overarching theory that makes geology make sense. It explains our volcanism. It explains our seismic activity, our earthquakes, and it explains the mountain building as well. And so these will be some of the topics that we'll get to in chapters 5 and 6. When we look at earthquakes, will be our next topic, and volcanism, so volcanoes and mountain building, will be in chapter 7. So we'll use what we learned with our plate tectonics. So you will want to review the different boundaries, the convergent, the divergent, and the transform boundaries, and review those. And then we will kind of put those together and dive in deeper with taking a look at earthquakes in chapter 6 and volcanoes and mountain building in chapter 7. So again, as always, if you have any questions, make sure you get with me, and always, go back and review your videos as often as you need. And I will see you next time. Bye for now.